All right, finishing up 6.2. So we did population growth, okay? Then we did decay, which we used to model radioactive decay. Remember that one, okay? The hardest part about that one is finding the A value, showed you how to do that, okay? And then after that, it's literally just plug it into the formula, okay? The last one for the models before we get into 6.3. One that you, believe it or not, should be a little bit more interested in than you would believe. Okay, we're going to look at it. It's called compound interest and the number E. Okay, realize they wrote this one a little bit differently here. Okay, compound interest formula. An investment of P dollars compounded N times per year at an annual interest rate of R has a value after T years of that. Okay, there's your formula. Well, this may seem like a very boring formula. Anybody here have credit cards? House payment? You got that? That's what they're using right there. Okay, that formula right there. Believe it or not, probably rules more people's lives. Not ruins, well, it probably does ruin a lot of people's lives too, because it's how they do your credit card statements. But it rules more of your lives than you realize. There's a big misconception about certain things, which is why I always kind of suggest at this level of math, I suggest almost every student should at least at some point in time, while it may sound boring to you, take a financial class. The math is no harder than this one. But the reason being is because everybody likes money, but nobody really knows how to spend it. Okay, well, they know how to spend it. Let's put it this way. They don't know exactly how to save it. So, or how it works. Okay. Hopefully today you're kind of going to get a little peek behind the curtain here. So looking at this one, we're going to kind of parse it out a little bit and I'm going to explain a little bit to you. An investment of P dollars, okay, that's going to be your principal amount. Okay, that will be the initial amount of money. Okay, remember that P of zero? They just don't use P of zero here. It's an initial amount of money that you want to invest, or it's also an initial amount of money that you owe. Okay, because think about it, if you have a credit card and you spend $100 on it, okay, average credit card rate right now is 25.9%. Do you know what that means? That means for every $100 you spend, they're going to charge you $25. Okay, that means you don't just owe them $100, you owe them what? $125. Doesn't sound like a lot until you realize that most credit cards come with, hey, we're going to give you an introductory offer of $2,000. Now, let me ask you something. This is a little good finance question. When do they charge you that interest? If I tell you it's 25% interest per year, when do they charge it?
Annually?
You'd think that, wouldn't you? Every day. Take 25% and divide it by 365. And that's how much interest they're charging you from the moment you swipe that card. The end of the day, you got charged that little bit of interest for that day. Now, you don't see it on your credit card statement, not until the end of the month, when your first bill comes due. And they go, hey, don't worry about it. Just pay the minimum interest rate. Or just pay the minimum payment. And you're like, sweet, what is it, 25 bucks? That's it? I'll gladly pay that 25 bucks. But go look at your interest rate. You spend $2,000 on a card, okay? You max it out, get new clothes, you look good for school. All that interest probably added up to more than $25. Just in 30 days. Now what's happened is this, is now they're going to say this, okay, that's cool, because guess what? Now you're going to pay that $25, that remaining balance that you owe, yeah, we're going to charge you interest on what you owe on that. So you never get out of the cycle. So the reason I'm showing you this is you guys can actually do this math now. Literally, by the end of this class, you can do this math and go, hold on, I'm not saying credit cards are bad. Dude, I got a wallet full of credit cards. Wallet full. I got a Lowe's card, I got a Home Depot card, I'm putting stuff on it every day. but I pay it off at the end of the month. I'm lying. I usually let it carry over a month, so I'm paying a little interest because that looks good on my credit report. After that, I pay it off because I know how much the interest is. I'm like, I'm not gonna pay you all that interest. You're gonna get a little bit from me. You're not gonna get a lot. But you can go in and use this formula right here and calculate it. Okay? So let's look at it. How does it work? Now, on the flip side of this, I showed you the bad part. Compound interest is good for this. Have you ever heard the term let your money work for you? This is what this is. This is why there's savings accounts. Okay, now I would not ever use a savings account like in town. My savings account's online, it makes me 3% a year. Or sorry, 3% a month. That doesn't sound like a lot. Putting up money in there, 3% adds up. Well, what that does is it says, hey, compounding interest says this. You give me $100 and I'm gonna pay you 3%, right? Well, that means at the end of the month, I'm gonna pay you $3. That doesn't sound like a lot, right? But the next month, I'm going to pay you what? Interest on what? 103. So therefore now, the next month after that, I'm gonna pay you interest on 106. It's compounding. It's your money working for you. You're actually making money on top of the money, the interest that you've earned. That's compound interest. That's how come you can have people who say, man, I started investing at 20, not me. I started investing at 20 years old and I retired at 40. Only by putting in like an extra $100 a month into an account, like an investment account. Okay, so that's once again, that was a very more complicated investment strategy, but it is compounding annually. Or actually, some of these compound daily, like your credit card payment. Okay, it compounds daily at like 0.05%, which people don't even notice until the end of the month. You're like, crap, look at my credit card bill. Okay, so look at that. So let's look at one. This is the difference right here. Look at this. I want you to see this example here. Maria has recently inherited $7,800. Most people just sock that away in a savings account. I'll tell you right now, a savings account in town is a scam. Don't ever do it. So until you take a financial class. Okay, because if you put $100 in the bank now, you only have $95 in a year. Okay, because that's what your money's worth in a year. Okay, you've actually lost money. Okay, it's called dollar cost averaging. So Maria has recently inherited $7,800. She's smart. She wants to deposit this into a savings account, but it's going to be a high yield savings account that you can find online. Okay, she had determined her two best bets are an account that compounds, now hear me out, compounds quarterly at an annual rate of 3.8%, which is awesomely high, and an account that compounds semi-annually at an annual rate of 5.5%. Which one do you think right now, using just what you think? You don't know. What do you think is going to make more money? The one that compounds 4 times a year? Remember, that means I have 100. That means after a quarter of a year, I'm going to pay some interest on that. I'm going to do it again. I'm going to do it again. I'm going to do it again. I'm going to do it 4 times throughout the year at 3.8%. Or is she going to make more money when it only does it twice a year, but at 5.5? Which do you think right now? Account 1 or account 2? 1. Everybody happy with 1? Okay, let's check it out. Math is super simple. You're going to need your calculators on these. Okay, no reason not to use your calculator on these. Why do that to yourself? It is good to go ahead and ensure that you write out the formula. It does make it a lot easier. So notice our formula is going to be, I'll write it right here. A of T is equal to that initial investment, 1 plus R over N and N T, okay? N being the times it's going to compound, okay? R being the percentage rate, and then T obviously being the amount of time, okay? So notice we have a p-value of this one, so let's go ahead and write A of T is going to be what? 7,800. That's not going to change, and this is going to be account number 1. The 1 plus is always going to be there. My rate for account 1, do not put in 3.8. Remember, put in 0.038, change that into a decimal, okay? Everything that we're doing in this equation is based off months, okay? So how many months is a quarter of a year? Hmm? You gotta do quarters because it's gonna do it. How many times is it gonna do it? 4 times, right? Okay. My N is obviously gonna be 4. What's my timeline? What's my timeline? You understand what I mean? So what they're saying, it's gonna be a year, just so you know, for 1 year. Okay, so you can just put a 1 there. Okay. On the time. N is how many times it's going to do that thing. Okay. The compounding. The time is how in what? In a year. Okay. But they may say this. How many times is this thing going to compound over 10 years? Literally, once you do that, you can say, hey, I'm going to invest this money. What's my money going to look like in 10 years from now? And he'll tell you. So we do all the math for this real fast. Okay. Put it all in your calculator. You should get, remember, round $8,100.65. Not too shabby after 1 year. You made what? $300.65 just in 1 year. Leaving it alone. Didn't mess with it. She said, here, I just want to make some money off this. It wasn't mine to begin with. Leave it alone. So then she says, hey, you know what? I did the math on that. Let's see how it would look the other way. We put in almost all the same numbers. We're just changing our rate and our time. Semi-annual will be how many times per year? Twice, exactly. So let's write it down with the N is equal to 2. Don't forget to change your rate. Your T would be a 1 in this, just in case, just so you know. Plus 0. What do we got here? 0.55, all divided by 2. And then over here we got 2 times a 1. You all said that it would be better for her to do it 4 times per year, but if you notice now, that little bit of interest does help, doesn't it? Because look, you actually get here 8234.90. So which account was better? Account 2. One of the few times in this class I'd probably say to you, this might be good to know next time you're talking to a car salesman. Hey, we're gonna offer you this interest rate. We're giving you a deal. Are you? I did it last time I bought a car. Really, it did. They were not very happy with me. I pulled up my calculator. I was like, hold on, let me check some stuff. I go, your math's not working. And the guy literally, it was funny because the look my wife gave was awesome. He goes, how would you know? And she went, I was nice. I was like, but sometimes the math won't work. And once you sign that contract, guess what? The math works. Usually by the math didn't work, I didn't like his numbers. I said, that math's not going to work. I go, I'm paying way too much in interest. I don't like that. So, well, look here. Maria has recently, keeps going, but says, how much would Maria's balance be from the account to over 2.6 years? Well, now she's left alone. She said, hey, I'm going to go with account 2 because obviously I made more money. Not just a little bit either. She made 100 and some odd, 100, like almost $200 more. Okay. It compounded less, but there was more interest. Okay. So she made more money. Okay. Don't get fooled into the more interest, more money thing. That compounding, don't neglect the compounding part. But then notice we're just going to do the same thing again. We've got a whole formula to work with now, right? Except what's changing now? We're going to change that T to 2.6. So we're going to have A of 2.6 is equal to 7,800 again. I got this 1 plus 0.055, compounding twice per year, all raised to the power of compounding twice per year times 2.6. How much would she have made in basically 2.5 years? Let's just say that, 2.5 years. Okay. She started out with $7,800. Okay. And she's going to end with 81.73. Why is compounding so good? What are we learning about? Exponential growth. This is literally what happens. This is not me trying to get financial. This is literally, if you take anything from any class, I always like to say there's one thing in one math class I teach every time that you're going to be able to take something away. I did intermediate. I do it really hard in statistics. And in this class, it's always kind of this lesson. I want you to really realize what's happening here. Who cares what happens here? But you invest right here. There's your initial amount, right? What does an exponential graph do? Does it just go up gradually? No, what does it start to do over time? Doesn't it start to get higher and higher and faster the more things move? It's exactly what happens whenever you do this, is it will start to do this right here. It starts getting faster. That means that money that she invested, do it over 5 years. It's not going to grow linearly. This little bit's going to go to here, and then to here, and then to here, and then to here. That's how come when you hear about somebody like they invested $100 a month starting at 20 years old. They retired at 45, but they just kept investing that $100. That money made money, which made money, which made money. And then they just kind of kept adding to it too, as well, you know? So it all kind of compounded. And next thing you know, you have somebody goes, man, I only invested like $200,000. How much you got in the bank? $1 million. I made $800,000. The interest alone compounded that much. Okay, that was kind of an extreme example, but it would be very easy to say you have 500,000 and only had to invest 200. Trick is leaving it alone. That's the hard part. You marry a greedy man or a greedy wife, they look in there and they're like, oh, that's a lot of money. We'd go buy a house. Yeah, we can also go get a loan and leave that money alone. So. Now, very rarely does this happen, but I want to show you another formula here. It does happen, so, but it's good to know. Continuous compounding formula. Excuse me. Notice they changed something on us. But either. Ask y'all once if y'all knew what E was. Okay, remember it's called Euler's number. Man named who went blind eventually while doing math. Okay. Not because of math. So I think actually it may have been because I think he would rub his eyes or something, you know, but it's back in the day whenever they used a lot of caustic chemicals. Named after him, genius of the number theory. We have a lot of things named after Euler and a lot of things we know about now because of him. He's kind of the one that developed this, and I want to show you this because I just would feel almost like it wouldn't be right for you not to know it. E, once again, Euler's number. You spell it this way, though. Okay? People want to say Euler. It's Euler because it's German. Okay? It comes out to this. It's just like pi. Pi is an irrational number, right? 3.1415 goes on forever. Euler's number is 2.71 and some change. It just kind of keeps going on forever. It's another natural constant in math. Okay? It's a constant of nature. Okay? It shows up everywhere. It actually shows up a lot more places than you believe. Okay? It's actually something you could derive yourself. You really could. If I said to you, hey, I give you this formula, 1 plus 1 over n raised to the n. Watch what happens as n approaches infinity. I'm just gonna write this out, you don't have to. Notice I just make n equal to 1, okay? If n is equal to 1, I get 1 plus 1 over 1, all raised to the first power. That's just gonna end up being 2. Okay, well, let's go up a little higher. How about I make n equal to 2? Then I get 1 plus 1 over 2 raised to the second power. I get 2.25. Go really big. What about n is equal to 1 million? Remember, we're going to infinity, right? So you want to see what something looks like when it gets to infinity? Plug in a really large number. Now, a million compared to infinity is how big? Really small. But to our minds, it's a really big number. So notice what's going to happen if I do this. Once again, I have this 1 plus 1 over 1 million, all raised to the 1 millionth power. And when we do that, 2.71828. And it just happens that way. Euler found this out, and they used it to model growth, continuous growth, okay? Your stuff doesn't do that. When I was talking about credit cards, that stuff is like compounded, not really compounded. The interest is charged at the end of a day. It's not like you swipe the credit card and in the background running, there's like this little ticker tape of like little interest, like constantly running at all times. That's not how that works. At the end of the day, they charge you so much interest. At the end of 30 days, they add up all that interest, and there's what they're going to tack onto your pay. Okay? This is a continuous, it never stops. They use it for modeling. Okay, this is used a lot for like modeling financials. Okay, you see it a lot when they start modeling, like this is what could happen to your money over time. Okay, but they'll use a lot for governments whenever we're dealing with like large amounts of data. Okay, it still works. Pretty neat. Let me show you a very simple one. Now they're going to be very explicit about this because notice how they say it. Tyra invests $5,200 in a new savings account, which earns 4.7%. I wish they would quit using savings accounts. I really do. It annoys me because there's no such thing as a savings account. You're going to get 4.7%. It really makes it. Well, I get 3.8, but you have to go online. Online banks are the best. Okay, just hand in hand. Compounded continuously. What will be the value of the investment after 3 years? That's literally, man, she's put money in and that interest rate is literally just going all the time. Okay, like continuously. You're going to want to use your calculator because your calculator does have an E button. Okay. Sometimes now when we get to the next chapter, they'll give you a value for E that they want you to use. Okay. Make sure to do, if they're telling you to use a value, use their value. Don't use your E value. Because your E is going to calculate like all of it. Everybody's going to truncate it. Okay. So make sure you use their truncated version. And for your homework, just so I don't want to see you get a bunch of red bars or get emails. We're going to change our formula. A of T is equal to P, Euler's number, RT. We have a principal, don't we? 5,200 times E. What's my rate? 0.047. And how long? 3 years. And all that can be put in your calculator. Okay. If you're going to do your calculator, I would suggest put that part in parentheses right there. Okay. Like when you're doing it, just put that part in parentheses. Notice after 3 years, I'm going to do the math for you. Go ahead and work out on your calculator. Make sure you know how to work it out on your calculator because remember the review, the questions I just did all up here, you might see on your final. That's how come I work these specifically. Did you get 5987.41? There you go. So how much would she have made? She made pretty good little money. I mean, it may not look like much, guys. I mean, let's be honest. You might look at that and go, dude, she only roughly made about $700, $787.41. But she made $787.41 doing what? Nothing. Zip. She put it away, and that's it. It sat there, and it made money. That's what they mean by your money making money for you. Okay? Now, what's neat about this kind of stuff, and now it's a harder deal, which is why I say go online. They have a thing called a Ramsey calculator. Dave Ramsey is kind of a braggart. I don't really like him that much. Call himself a Christian, but then he makes fun of people. I don't like that. But he is really good in finances. Okay, so it's sort of like one of those people you're like, you're a piece of crap, but you're pretty smart. Go in there and test it out sometimes. I don't care how broke you are right now. But go in there, everybody says they're broke, and all of a sudden I see them walking around like Starbucks. Okay. I'm not broke, but they pay us good. Look at it and see what would happen at your age right now if you said, I'm gonna put $20 away every month. Okay, they call it dollar cost averaging. It doesn't matter. I don't care what you just turn off the news. If you find an investment, I use this is not since it goes on YouTube, I want to make sure that I'm not giving financial advice. Do not, let's put a little disclaimer out there. I use Charles Schwab just because they have a thing called themes. So if like you're big into AI, you can just say, hey, here's $20 invested in AI companies. And they'll take it and they're like, all right, we got you. And leave it alone. Forget about it. Don't ever look at it. Don't ever go back in and look at it. And then every month, just sock away $20. If you get a better job one day, maybe get a little more serious about it, like maybe go talk to a financial advisor. Keep socking that away and watch how it grows. And whenever you hear about, man, AI took a bomb today, sometimes you might go, hey, I might add a little bit more to that. Like I love it when I hear about the market failing. I'm like, sweet. I invest more money because I don't plan on saying anything else. I retire anyway. So when things drop in value, what does that mean? I'm getting more for my money. So, but that's because I think of this right here. I make enough money now to live just fine. But what about later on when I don't have this job? I'm like, I'm going to keep this job until I probably die while teaching math. But still, it'd be nice. So think about that, or think about taking a financial class here, like with our professor, I think it's Chalaka. I'll take one with him. This is an introduction to finance. All right, we're good? That's exponentials. Okay? Take a deep breath, because no one likes logarithms. Okay? Because they get weird. Okay? Logarithms are fun. But I'll be honest, even whenever I have to get ready to start teaching logarithms, I have to go back in and go, okay, let's get ready for this. Because remember, like I told you in the last class, you're in what we call transcendental, okay, type of functions. Okay? Transcendental because they transcend your normal algebraic behavior that you're used to. Okay? While the rules of math are still there, you're having to do some different ways. Like in the last one, how we're having to change those bases around, try to make the same base. You're not used to doing things like that. And so your brain's going, what is this? Okay? I want you to kind of think of that as we move forward. Okay? So here we are, logarithms, finishing 6.2. Logarithmic functions and their graphs. While I would really love to just honestly, I would love to take 2 full class periods on this one. We really don't have time. Okay, we only have, and let's say that we finish up next week and then you're losing out on review time for your final. Notice as we jump into this. When we started learning in 6.1, I started teaching you how you could solve the equation 2x is equal to 8. First off, can anybody remember what do you have to do to that 8 automatically?
Change it to a 2.
Yeah, change it to a 2, but not just a 2. 2 to the power of 3, right? You want to make sure it still equals out to an 8, right? So you have to change it. We're trying to match bases, okay? So realize we could write that out as, okay, 2 to the power of 3. So then we get 2x is equal to 2 to the power of 3. And then we make the exponents equal to each other and solve, like we normally would any other equation. We would come here and put x is equal to 3, and there you go. And that's how it would work every time, right? When you were solving those elementary ones, worked out fine. What do you do for 9? I mean, can we all agree that something you can multiply something to this to get to the 9? But what? That'll just give me an 8. I don't get to the 9. That statement wouldn't be true. Okay? So there's a problem. Another problem exists is, and I'll show you in your notes, I show you this. Do I show you this? I may have it on your, I think I have it on your notes here as well. I'll get down to it. Notice on this one right here. On one of them, if we know the A, P, N, and T, we can solve this. Okay? If I give you this, this, and this, no matter what, I can solve the whole thing, can't I? I can switch things around, I can solve for things. How are you going to solve for R? It's a little weird, doesn't it? So, look very carefully. First off, I want to go way back in time. Remember the whole, could anybody tell me, is there an inverse? This is a function, right? This right here is my exponential function, which is, this is f of x is equal to a to the x. Can we all agree with that? That's what the base graph looks like, right? This would be for greater than 1. Remember, because less than 1, it would be going in the opposite direction, but still it's an exponential graph and it's an increasing function because it's getting larger. Hence, that's what I was trying to talk to you about your money. Look at that, you invest low, but it goes up quick. Does it have an inverse? Think back. How do you know if it has an inverse? There's a test. I gave it to you. Remember that little horizontal line test you could do? If it only hits once, you have an inverse, doesn't it? Because remember the parabola? A parabola is a function, right? But the inverse was what? It was a parabola on its side. But when you do the parabola on its side, it's not a function anymore. And so therefore, a parabolic function does not have, or a quadratic power of 2 function does not have an inverse. Unless we bound it. Remember, like I showed you how to do that a little bit. This one does. This one does have an inverse of it. Without showing you the math, because it would get messy, remember there's a way to find the inverses. Here's the problem. Remember we have the f of x is equal to this, make f of x y, then switch the x and the y. That doesn't work for this, okay? So now you're going to have to learn a new function, okay? And it is the inverse. Hear me out. This is the inverse of an exponential. And it's called a logarithmic function. Logarithmic functions, okay? Let a be a fixed real number not equal to 1. The logarithmic function with base a is defined to be the inverse of the exponential function with base a, and is denoted log a of x. In symbols, if f of x is equal to a to the power of x, then f of negative 1, remember that's that little inverse symbol saying, hey, this is the inverse of that guy. Log a of x. In equation form, the definition of a logarithm means this. And there you go. X is equal to a to the power of y. And for the other inverse, it's y is equal to log a x. Note that a in both equations are both the base. Okay. That's a lot of mumbo jumbo. Let me show you. Let's do some definitions here. It's not as bad as what you think, but it's going to be confusing because you're not used to writing these yet, okay? And about the time you get used to writing them, you're going to leave this class, and then you'll forget all about it. Till one day you see them here. Damn it. Look at how I'm going to write this. Okay. I have 2 to the power of 3 is equal to 8. Okay, here's what we do. We're going to have, first off, you always write log. Log. This is always your base. Remember, that's the base of your exponential, isn't it? I don't care where they put that equal sign. The base of the exponential is the 2, right? Okay, so that's always going to be your base, and it's going to be sitting below. Then you don't put the power next. It's always what, excuse me, it's always what does this thing equal? Well, the equal sign goes right here, the equals 8. So log base 2 8 is equal to 3. Now, I did this all over your notes. Watch this. Two-thirds is equal to 8. Notice 2/3 is equal to 8. That's how I used to remember it. The 2 comes up to the 3 and jumps back, going across that equal symbol. Okay? This is an inverse. Okay? Do the next one. Write it out, see if we get it. Okay? Your base is the 5. And you have an exponent of 4. The good news is I don't want to be jumping around colors. On your notes today when I download them, I color code a lot of these in the beginning. Okay, it kind of helps out. And it helps you color code them. You have log. What's my base?
25.
Hmm.
5.
5. It's always the base. That log 5 is always the base of your exponential. Okay? And then it's my equal. What am I equal to? 625. Same as this way. What power of 5, what power do I need to get to that 625? That's kind of what it's asking right now. You got this base of 5 and it equals 625. What do I need to equal to get to that 625? And they give it to me. You need to equal 4, which is why you can draw that line here of 5 to the 4 is equal to that 625. Okay. And then last but not least, we'll do this last one real quick. I'll just kind of write it out. Notice I have always log, always lowercase. Log what? Log of 7. What do I put next?
Z.
Z, exactly. Is equal to what? X. So remember this part here. There's your exponential. There's what it's equal to. Okay? And you can go backwards. Now notice if you do my lines that I just did, it kind of makes it easy, doesn't it? If I said, hey, write this log, but write it in exponential form, well, can I not just draw this to here, right? And doesn't that just give me, hey, 3 squared is equal to what? 9. How about this one? Don't worry about how they wrote it. Rewrite it if you need to, because they're trying to fool you. Rewrite this as log 8, 5, 12 is equal to 3. How about this? 8 to the 3rd is equal to 5, 12. Once you get that, can't you just do this? And for this one right here, you get 2 to the y is equal to what? X. You see how maybe that drawing that line helps you a little bit? Your base is always going to be your base of your exponent. And then you're always going to have it equals to, that's going to be the x, that's going to be the power. And then you got the equal. Did you do that with some practice? Okay, let me show you some stuff here. I have two different logarithmic functions here. One of them is a decreasing function. Notice it's going to be your blue line. Look at the blue line. Okay. Because the blue is the log. Okay. The other part is your exponential. And then notice, is that not your line of that if you folded it, it would do what? Remember, it would go away, just become an X. Remember whenever we multiplied or we composed functions together? That's what would happen. I do want you to notice something here about this line. You have a range of all real numbers. Okay, now this is for one. A is between 0 and 1. It cannot equal 0. Okay, it's asymptotic there. If it equaled 1, wouldn't do anything. Okay, you'd have a constant. Don't need it. Okay. Notice though, look at the range, look at the domain. Okay, range, all real numbers, doesn't matter, right? Look at the domain. While it looks like that is going to cross the y-axis, it does not. Okay, so your domain is from 0 to infinity. Okay, that's important. That means you have restrictions. So when you're solving for these later on that I'll be showing you, you have to make sure that you solve, because you may say in your homework, hey, if this thing is undefined or whatever, you can't equal it, let me know. Well, when you're solving it and you get a number that's less than 0 or not inside the domain you solve for, you gotta know for it. Like if I gave you x plus 5. Well, x plus 5, you wouldn't make it equal to 0. You say x plus 5 has to be greater than 0. When you solve, that's how you would do it. Just make sure you make things greater than 0. Okay? Think about what you did whenever anytime you dealt with a restriction. Logarithms have restrictions. It should kind of make sense if you think about it, because look at the graphs of it. Okay? How are you ever going to get a negative number whenever you're taking things to powers? You know, that kind of makes sense. You can, even if you have a negative exponent, what do? You don't get a negative exponent. They just turn into a what? A fraction. That's what negative exponents do. They don't work the same way as like a negative base. Okay? And you can have negative bases all day long. Who cares? Okay? So, here's the other one. This is an increasing function. Notice once again, this is for when a is equal to 0. This is going to be helpful whenever you are graphing. Okay? Just kind of know the shape. Notice no matter what though, it always went through 1. So when you're graphing these later on, if you realize it always goes through 1 right there, hey, think about it. Whenever you start translating these things backwards and forwards, you can go, if I can start here, I can go here to here, here to here, up and down. Or you can always plug in numbers, still just like with exponentials, use 0, 1, and -1. Those are the easiest ones. Reason being is because these are the exact opposite of an exponential. An exponential does what? Very fast. Remember, it grows, right? An exponential function grows very fast. So what do you think a logarithmic function does? It grows what? Slowly. Does the exact opposite. It's an inverse. Notice what's going to happen here. If I kept drawing this guy, it's going to look like it evens out. It's almost going to look like a straight line. It is not. It's just growing very abysmally slow. Logarithms grow really, really, really slow. Okay? They're one of our slowest growing functions. Okay? Evaluate the following logarithmic expressions. Okay, I'm going to show you ways to do this. I'm going to do these pretty quickly, but I'm going to show you how to make it easier on yourself. I pulled these from the book, and I did it for a reason. You can go look at the examples in the book, but they're not explicit in how they came up with their numbers. Okay? They just kind of go, and here's the answer, happy birthday. And I'm always like, well, that's kind of mean. So let me show you here. notice some of them you can just kind of look at and just know. Okay? But notice here I've got log 5 of 25. Well, that would be the same thing as say, okay, log 5 of 25. Well, couldn't I just say this? Log 5 and change that 25 into 5 squared, right? And so that means this guy is equal to 2. Right? Because hey, 5 squared is what? 25. Isn't this guy right here? Isn't that 25 5 squared? Okay. Now, let me help you out here. Do it this way. Go back to chapter 1. Not chapter 1, sorry, 6-1. If I gave you this on one side, 5x, you do not know what that is yet, do you? Is that not what they just gave you? There's something over here. I don't know what it is. But can I not change that 25 into what? 5 squared, right? Just like you did in 6-1. And so when I do that, I get 5x is equal to 5 squared. And then what? X is equal to what?
2.
There's your answer. Kind of help you out a little bit on that one. You kind of see it a little bit better now. If you change it back into exponential form, kind of makes it easier to solve. Let me show you the next, and I'll show you. Let me give you a little hint too, by the way, if it helps. I'm going to say it now because it'll save on time. And let me just tell you, this is universal. It always works. Does anybody notice something that just happened? Let's see if I will see if anybody notices. I always like to see if people can notice it. I got, what is x equal to? 2. In doing my solving, did you see a 2 pop up anywhere? What went away? Those cancel out. Every time. If your base matches an inside base, so let's just kind of put it that way, those cancel out, you're just left with the power, and that's going to be your answer every time. Watch, I'll prove it to you. It's kind of neat because trust me, it makes the math super simple. Okay, look at this next one. I've got log to the 1/2 2. Well, let's realize that that's actually equal to x, right? Can we all agree with that? Technically, is it not actually be equal to y? Okay, I'm just saying x right now just for clarity for you. Okay, so let's come in here and let's actually write this like this. 1/2 x is equal to 2. Well, let's be honest. I can't change that, but I could, couldn't I? How would I make this guy a 2? Can't I bring him up? Am I allowed to do that with the laws of exponents that you know? Think about it. Couldn't I do this? Watch. How about 2 to the negative 1? Don't those mean exactly the same thing? 2 to the power of negative 1 is the same thing as saying 1/2. Right? All to x is equal to 2. There's a power there with that 2. What would it be?
1.
Yeah, a 1. Well, don't I take that negative 1, multiply it to the x, and so therefore I got negative x is equal to what? 1, which actually is going to be what? X is equal to negative 1. There's my answer. Right there. That's what that would equal. Makes sense. Hear me out. Why does that make sense? Look at 1/2 to the negative 1 power. Isn't that what that's saying? If I take this power here, it should equal this, right? Well, doesn't that just turn into, okay, well, 1 to the negative 1 power, 2 to the negative 1 power. Well, that 1 to the negative 1 is going to go down. That 2 is going to go where? up, and that's gonna leave you with 2. See? So it works. How about the 4? The 4 was, I'll be honest, the 4 was the one I was like, oh, this is gonna lose them. Until you do it the way I just showed you. Okay? Look carefully. Like I said, this is how come these are transcendental. They're a little bit more weird. Let me give myself some room here. Once again, I have log 4 to the 8 all equal to, I have no idea. Right? Well, let's look at this. I can come over here and notice that I have got what? 4 to the x. And then I've got what? 8. But can I, you should see this now because this is literally chapter 1 stuff. Right? Isn't that just 2 to the power of 2 x all to the what? 2 to the what? Third. Make your exponents equal to each other. So I get 2x is equal to 3, which means x is equal to what? 3 over 2, and there's your answer. Wouldn't it work? If I take the square root of 4 cubed, well, think about it. 4 cubed is 64. The square root of 64 is what? 8. And then the last one, you got pi. Like, oh crap. I got symbols. I hate symbols. But why? For one, you can do this. You can either say, hey, A, I'm either going to listen. I do want to show you this real quick. Remember I told you about the base thing? Look at your last one. If I have log here, right? Log 4, let me see here, would that work? And notice if I came in here and I was just able to change it. Let's just say you knew. And you change this to log 4, 3 over 2. Don't those mean the same thing? Don't those cancel out? That's what that equals there. Okay. The hardest part was finding that guy there. So that's how come I said, do the other math. Put it back in exponential form and solve for it. Okay. But the bases are still going to go away. Okay. So look at this next one here. I have log pi square root of pi. Well, let's just put an x out here. And really, when you really look at this one, look at it very carefully. Don't I just have pi over what? To the x is equal to pi what? Change it.
Squared.
How do you change a square root into an exponent? Remember that? The 1/2 power. Remember that? Your denominator is always your what? Your index. Okay? And then you got that power on top. Hey, doesn't that just mean x is equal to what? 1/2. There's your answer. So if you rewrote this thing, you would have this log of pi to the 1/2. So really, if you just knew how to rewrite that, what happens to those pi's? They cancel out, you're just left with 1/2. There you go. Are you okay with that? Probably gonna need some practice on that, aren't you? Okay, because it is weird. It's something you haven't done before. Hence, the transcendence of all this. Need to kind of kick it into gear just a little bit, if you don't mind. Because I do want to make sure we get through this one. Let's take a look at this one here. Use elementary properties of exponents and logarithms to solve the following equations. I want you to be very careful with this one. I'm going to work through these very quickly, but you can go back to my notes, okay? Sometimes when solving for these, it's easier to change them back into another form. Okay, I want you to notice this first one. This first one is log 6 of 2x is equal to -1. Can I not just go ahead and rewrite that as an exponential like we just did? And if I did that, I would say, hey, 2x is equal to 6 to the negative 1, right? But can I let's just be honest with that and say, hey, I need to change that around. How about I do this? How about I get 2x is equal to 1 over 6? Because isn't that what that negative 1 does? Can I just solve this right away? You should be able to solve for x pretty straightforward and simple, right? Multiply both sides by what? 1 over 2. And we're going to get x is equal to 112. And there you go. And like I said, by the way, on the other side, there should have been a y there where I was solving for x, but I don't want to muddy the water with changing variables on you right now. Because remember, the x is actually embedded into that part right there, okay? It's when you do an exponent, it's always the y on the other side. Remember, it's an inverse, okay? Look at the next one. If you look this one up in the book, if you're not careful, you're gonna be like, I have no idea how they got that answer. Okay? But realize what they're doing is I'm gonna change this from exponential form. Is that not what form it's in right now? Exponential? Well, how about we change it back to logarithmic? And notice how, now hear me out. When you're doing logarithmic, when the bases are the same, remember the little subscripts are the same? You make those equal to each other and solve. I'll show you. Notice for this one, to solve it, I would say this. I'm going to bring down this whole other part here. I'm going to have this log 3x2 is equal to log 3, 2. It makes sense if you look at the definition. If I've got a to the b is equal to c, then log a c is equal to b. That's how come I rewrote them that way. Okay. Like I just said, if you have the bases here, notice I can just make those equal to each other. Because do they have the same base? There's a 3 there, isn't there? Yeah. So I can make those equal to each other. 3x is equal to 3. When I do that, what am I going to get? X is equal to what? How about 1? 3x is equal to 3. Divide 3 by both sides. You just get a 1. Remember, on one side, I literally just wrote it. I rewrote it. I rewrote it like a logarithm, right? Okay. I put the base down below. Now let's do the next one. This one, once again, because it's already in logarithmic form, I'm going to change it into exponential form. Okay. So notice on this one, I have, well, let's look at it carefully. I have 2 to the 5th is equal to, well, let's just be honest here. I have 8x, right? So I have this. Well, let's be honest. What do I need to do to that 8? Change the base, right? So how I've got 2 to the 5th is equal to, how about 2 to the 3rd, put a parenthesis, put equal to x. And then now, once again, like you did in 6-1, make it equal to each other. Okay, so I've got 5 is equal to 3x, and we're going to get x is equal to 5 over 3. Play with that one. Saw a bunch of confused looks on that one, but rewrite it.
I just didn't see how you rewrote it into 2 logs. That just didn't make sense to me.
Reason being of it is, look, on one side, you've got to equal to each other, right? Okay, you got to think about you're rewriting this as a logarithm, right? And a logarithm is always equal to something, correct? Okay, so look at the formula over here. If I have a to the b, well, don't I have an a? That's my what? That's gonna be my base, isn't it? So I go ahead and put log. Oops. Okay, what's my b? It's always gonna be log 3, right? Is that not my base right there? So it has to be log 3, does it not? Okay. Log 3 what?
2.
Exactly, you put your 2 next, don't you? That's why you get the log 3, 2. What does it equal? It always equals the what? The exponential. Your exponential is that whole other log that's on top, and that's why you get the log 3x 2. That can help you see it a little bit better now.
Yeah, instead of the exponential just being a little number, it's a whole log. So that's why we take it out like that?
Yeah. Yeah, because it's saying you're equal to this whole thing.
Yeah.
Imagine it this way. If I had to put a 4 there, you'd have put a what? A 4 right here. Except there's not a 4 there. There's this whole other log that's sitting up there, and so you've got to make it equal to that. Does that help you out a little bit better on that one now? I saw some confused looks, and I didn't want to just gloss by it. I wanted you to see, and that's how come I put this here. Okay, and it is tough to see it because when you've got all these moving parts, it's sometimes hard to tell what's going on with what, okay? But just remember, log, okay, base 3 is equal to 2. That's simple enough. Okay, but what's the power? Remember, the power is always your C value, which is that guy there, and that guy there. Okay? Better? I said, don't want to gloss over anything. I'm gonna be honest, we're not gonna have time. I can do a couple tomorrow, but the next 2 lessons are still pretty in-depth like today. But I have a bunch of a ton of examples in the notes. Okay, that I'll download today. Gotta finish up these last parts. And then we're done. Are you okay with what we just did? More or less, it's gonna take some practice. Yeah. You got a lot of practice on this homework, by the way. Okay, there's about 24 questions. Okay. Look carefully here. Let's finish this up. Common and natural logarithms, okay? This is what I want to tell you. Okay, and these you're just gonna have to memorize, guys. And you are gonna need to know these, okay? Unfortunately, because you don't have time to like mull this over the weekend and we'll come back next week. No, guess what? Kind of have this in your head by tomorrow. Okay, the function log 10. Now that is base. Your calculator only works off log 10. Okay, if you look at your calculator right now, you'll see a log button. It's always basing itself off log base 10. Okay, that's the log button. Right here, log. Are we good with that? Always base 10. It's important to know that later on, okay? Natural log is always base E. There's the other one on there. It's right beneath your log button. It'll have an LN. It's always base E. Okay? The reason I say that is if you see, okay, log X, and you don't see a base here, it's a 10 every time. Okay? So you need to put that into your head. No base, log 10, okay? With a log E to the X, you're gonna have, we use the word ln, natural log, okay? It's always basic. They are the exact same thing. Look at them carefully. Are these both not logarithms? They're both written the same way. You do the exact same math to them. But we just have to have some way to differentiate them, okay? And these are base log. That's a log base E, okay? What makes this nice is if you go back and remember what I said. When the base matches what's ever in the parenthesis of its base, okay, what's going to happen?
Cancel.
They cancel out. So let me show you something. Like I said, very quickly, I got 7 minutes. I have the natural log here of 3 of the cube root of e. But realize, what are we seeing here? We're actually seeing what? Log with a base of what? E. Well, couldn't I rewrite this as what? E. My index is always my what? Denominator to the 1/3. What is going to happen to those e's? They cancel out, reduce out. And so my final answer here is just going to be 1/3. See? Notice the same thing here. Watch what's going to happen here to this log. Since you see log but no base listed, what do you know it automatically has to be? Log base 10. Okay, so let's rewrite that. If I have log base 10, rewrite that. Can I put that as 10 to the 3rd? What's going to happen to those 10s? Once again, those 10s reduce out, cancel out, whatever you want to say. Whole is equal to 3. All of that you're able to do with that calculator. Because guess what? On your final, there will be something on there. I'll say, hey, calculate this without using your calculator. It says it all over the place in your homework. Because a lot of this is just going to be the, hey, just can you do this simple math? Now, here's where it gets weird. Can't do those. So try it in your calculator fast. Do the natural log. Look at your yellow calculator or the calculator you have. Make sure to see if you have an LN button. If you don't have an LN button, you got problems. And you're literally just going to type in LN, and it's going to give you a parenthesis, put 4.78. And you should get 1.564 dot dot. Did you get that? Do log 10.5. Log would have a base of what? 10, exactly. And then you just put in your 10.5, very simply, and you should have gotten 1.021. If you're rounding to right there, you should have got 1.0211892, but then I rounded. And that is how you deal with logarithms. Okay, that is our example. I have a few more minutes. Let me scroll to the very bottom just to help you with one question that I know you're going to have. Like I said, I do have a bunch of examples on here. Okay, some of these, like these first two, super simple. Look at that 121. Could I not write that as 11 squared? What's going to happen to the 11s? They reduce out and you're only left with a 2. There you go. You solved it right in your head. Go impress your friends and family. Let it be a party trick. You won't be very popular. I do math tricks all the time. People just look at me. You got some in here that are weird, like that one. It's not as bad as what you think. Okay? Especially whenever you start realizing you're doing what? Some things are going to cancel. Then you're left with something. You just do it again. It's sort of like working from the inside out. Okay? All these are worked. This one right here, I want you to be very aware of. That 7x plus 6, when you're solving for these, always make sure that you do what? Make it what? Greater than 0. Remember to solve for the, remember domains? Got to make sure that you don't end up with a restricted value. That means if you end up with a restricted value, you have no solution. Okay? So just kind of be aware of that. Here, right here. I've got 2 of these like this one. I think I've got 1. Nope, just 1 for y'all. Super simple. Okay, if you just look at this one, just I want to show you how to graph. First off, let's remember, okay, look at the base. Okay, the base is greater than 1, isn't it? Okay, if the base is greater than 1, I got 3 minutes. Go all the way back up, look here. Base greater than 1, hey, that means my graph better look like that guy right there. As its base graph, right? Just the base graph. It's an increasing function, it looks like that. So that means I can come back down here. And do you see one that does not look like that? Yeah, look at that one. He's not gonna work. Immediately, he's not gonna work. All the other ones, okay, well, let's think about it. I know a logarithmic always goes through what?
You want-
Here one, let's look at it very carefully. Look at it, come back up here again. What's that? 1, 0. 0, 1 for exponentials. 1, 0, remember they're inverses. 1, 0 for logarithms, okay? Well, if I know my base function goes through 1, 0, just 1, 0, I know that I should be going through a 1. But then guess what? I've got that what? X minus 5. X minus 5 says what? What are you going to do? Move up, down, right, or left? Right. Exactly. You're going to be moving right how many places? 5. So which one does it?
First one.
Does it? Moves right or does it move
Oh.
left? See that guy right there. Because look, it moves over 1, 2, 3, 4, and there's my 5th spot right there. Now, how would I know if it went up or down? Out here, you can see like a +1. Okay. Now, if you saw that +1 out there, then you start doing what? Up or down from there. Whatever's happening inside the parenthesis is deciding whether you're going to go right or left. The base is going to decide what type of like, are you going to have, once it gets below 1, you're going to have a decreasing function. Everything else is going to be just how skinny is that thing going to get, kind of thing. Okay. That can help you out a little bit. Also, what you could do if you wanted to, you could always graph. You could come in here very easily and go x cube of x. What if I plug in 6? Well, how about the log 4 of 6 minus what? 6 minus 5 is what? Well, how do I get 4 and how do I make that equal to 1? Exactly, because anything to the 0th power becomes a what? 6, 0. You see a 6, 0 on my guy there? There he is. So notice, like I said, just so that was a quick little how to graph them really quick. Okay. And that's how you'll do them on Hawks. So how do you feel about logarithms? They're a little weird, aren't they? They're probably one of the weirder things we've studied in this class. Exponentials you kind of get because you've seen them before. You know, even if it's just x squared, you can kind of have an idea. These, the math of them is a little weird, having to know how to do the bases. So just do the best y'all can. Email me. I've got, like I said, I've got a ton of examples on here. Okay. But don't be afraid to hit that solution button. I hate to say it. Sometimes that solution go, okay, that helps out. But also, I'm an email away. Okay. And then next week, remember Monday and Tuesday, we'll go over review. Tomorrow, 6, 4, 6, 5, and we're done. Okay. Well, not tomorrow. Tomorrow, the next day, 6, 4. I'll see you guys later.